Okay, this is a lesson on introduction to the concept of equilibrium. Now, I might have provided the slides to you, and if I have, then I would print out the slides in as a handout. So you have 4 or 6 slides on a page, and then make notes as we are going through the lesson here. So that's kind of reflective of what a professor in post-secondary would or how they would probably deliver their material to you. Okay, so if we think back, most of the chemical reactions we've discussed so far, the reaction goes to completion, and almost all of the reactants are changed into products. So we've always told you that a chemical reaction is one that cannot be reversed. But today I'm going to tell you that is actually a lie. But most of the reactions that we have been dealing with so far in chemistry look something like this. A and B react to make AB. So the symbol, this arrow, means that it mostly, about greater than 99% of AB gets converted into the product. Sometimes, if we look, AB going backwards gives us no reaction. So that's telling us that less than 1% of AB will go backwards into making A plus B. And so because very little of it will actually go backwards into making A plus B, we say that it basically, the reaction goes to completion and all of the reactants are made into product. Now, the reality for a lot of reactions is that they actually take place in both the forward and reverse direction at the same time. So what that looks like is while some A plus B are being converted into AB, some of this AB is going in the reverse direction and going back into making A and B, A plus B. If the reaction is going to occur in the reverse direction at the same time, we use an arrow that looks like this. It's a double arrow. So if you have a situation with a chemical reaction, if you leave it alone long enough, it reaches this state called dynamic equilibrium. So this dynamic equilibrium is important to us. A chemical equilibrium is when the forward reaction and the reverse reactions are balanced and both reactions are occurring at the same time. So some reactants are turning into products, and at the same time, some products are turning back into reactants. If we were to graph concentration of some substances at equilibrium, it looks like this. So we're going to look at this reaction. Nitrogen gas plus hydrogen gas is making ammonia. If you look, the reactants, hydrogen does this. We start with this much hydrogen, and it gets down to this point where equilibrium is reached. And at equilibrium, the concentration stops changing. So hydrogen decreases in concentration, which makes sense because the reaction is going to make some NH3. The nitrogen concentration starts here and it goes down a little bit, but once it reaches equilibrium, the concentration of the nitrogen stays the same. And then NH3 does the opposite. It starts at 0 and it grows. The concentration gets bigger as the forward reaction is happening. And eventually, At equilibrium, same idea. It stays constant. So when a system reaches chemical equilibrium, so when the forward reaction and the reverse reaction are both happening, the concentration of the reactants and products stops changing and stays constant. This is a big one here, okay? So I would even maybe highlight that at chemical equilibrium, concentration of products and reactants stop changing. It's consistent. So chemical equilibrium can look like this. A dynamic equilibrium. It's a chemical system at equilibrium. So just think of when we say chemical system, you can kind of just think of a chemical reaction that is changing at the molecular level while macroscopic properties remain the same. So what that means is that if we could zoom in and look at the molecules, some of the reactants are turning into products, some of the products are turning back into reactants, but we can't tell that there is a change happening because they're happening equally. So here's an example of a dynamic equilibrium. If we have a glass of water, what we know is that some of the water is evaporating out, but some of the water vapor in the atmosphere is condensing back into the water glass. This is a dynamic equilibrium. We cannot see the change in amount of water in the glass because it's not changing. But if we could zoom in and look at the particles, some of the water is evaporating and some of the water vapor is condensing back into the water glass. So there's changes happening at microscopic levels, but at eye level, we cannot see a change. That is a dynamic equilibrium. Another example of dynamic equilibrium is the fact that water being transported out of a cell in your body is almost the same as the amount of water being transported into the cell. In fact, you owe the health of your body to dynamic equilibrium of water. Okay, so if we have a system and we want an equilibrium, there are some factors that are required. So the first factor is that we have something called a closed system. In order for an equilibrium to happen, the forward reaction rate, so how quickly reactants are turning into products, has to equal the reverse reaction rate. So products have to be converted right back into reactants at the same reaction rate. When you are at equilibrium, the concentration of reactants and products are constant. When we say constant, we don't mean that they're equal, because they're probably not equal, but they're plateaued like we've seen in that image. Temperature and pressure have to remain the same. And this is a big one here for number 5. An equilibrium can be reached by starting with the reactants or the products. So what that means is you can get to equilibrium from either direction. And then finally, macroscopic properties. So what we can see at eye level, such as color, pressure, concentration, pH, of equilibrium are constant. There is no overall change in any of these properties once we have reached equilibrium. On the way to meeting our equilibrium, so when we saw that change in hydrogen concentration and change in NH3 concentration, that the macroscopic properties are changing while you are approaching equilibrium. But once you get to equilibrium, so the state where forward reaction is occurring at the same rate as reverse reaction, you no longer have any changes to these properties in 6. Okay, so We can have equilibrium, a couple different kinds of equilibrium. One of them is in a physical system. So when a pure substance undergoes a change of state and achieves dynamic equilibrium, it's known as a phase equilibrium. And it's a phase equilibrium because it's turning from one phase to another. A really neat example is solid iodine in equilibrium with iodine gas. And we can see that right here. It's like a purple solid that goes into like a purple vapor and then back down. And then we already seen this example with that water glass, but liquid water in phase equilibrium with water vapor. So when the equilibrium is between a pure substance in different states, it's called a phase equilibrium. And then we also have a homogeneous equilibrium. So this is when all the states are the same. So in this example, we have but all of the reactants and the products are gas. And then our heterogeneous equilibrium is when the states are different. So our phase equilibrium, where liquid water went to water vapor, that's a heterogeneous equilibrium because you are changing state. Okay, so that is the end of our introduction to equilibrium. So the big takeaway here is that in a lot of chemical systems, the reaction doesn't go to completion. Because what ends up happening is at some point, the reverse reaction starts occurring at the same rate as the forward reaction. And so reactants and products are both being produced and consumed at the same time. The overall concentrations of the reactants and products do not change once the system is at equilibrium because the production and consumption of them is at an equal rate. Okay, we're going to talk more about equilibrium in our next lesson, and then we're going to start looking at equilibrium quantitatively, which means we're actually going to start calculating out concentrations of substances at our equilibrium.